Hello everyone. Welcome to my YouTube channel on engineering mathematics. In this video, I'm going to discuss various examples on hyperbolic functions. We will use the relationship between hyperbolic functions and circular functions as well as their identities in these examples. So let us first see prerequisite. Over here, we will recall the definition of hyperbolic functions, the relationship between hyperbolic and circular functions, their exponential forms, and identities. First, we see the definition. The functions which satisfies the equation of the hyperbola, say x square minus y square is equal to 1, are called as hyperbolic functions. Euler's exponential form of hyperbolic functions is as follows. Cos hx is e raised to x plus e raised to minus x upon 2. Sin hx is e raised to x minus e raised to minus x upon 2. And tan hx is e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x. The relationship between circular and hyperbolic functions is as follows. Sin h ix is I sin x, sin ix is I sin hx, cos h ix is cos x, and cos ix is cos hx. Some of the identities of hyperbolic functions are cos h square x minus sin h square x is equal to 1, e raised to x is equal to cos hx plus sin hx, sin h of minus x is equal to minus sin hx, and cos h of minus x is equal to cos hx. Note that we have seen the proofs of these identities relationship in my previous video. Link of that video is given in the description box. Now let us go ahead with some real examples. In this example, we are asked to prove that cos hx minus sin hx whole raised to n is equal to cos h nx minus sin h nx. Let's go for solution. In solution, we proceed with LHS. LHS is cos hx minus sin hx whole raised to n. We will make use of exponential forms of cos hx and sin hx over here. After replacing cos hx and sin hx by its exponential form, the RHS becomes this. Now let us simplify this bracket first. So we have e raised to x plus e raised to minus x minus e raised to x minus into minus plus e raised to minus x. So this e raised to x and minus e raised to x will get cancelled. We will left with 2 times e raised to minus x in the numerator and 2 in the denominator. Whole raised to n outside as it is. This 2 and this 2 will get cancelled. So we have e raised to minus x whole raised to n, which is nothing but e raised to minus xn. Now coming on to RHS. RHS is cos h nx minus sin h nx. Let us replace this cos h nx and sin h nx with its exponential form like this. Once again, simple algebra will give us expression 2 e raised to minus nx upon 2. Once again, this 2 and 2 will get cancelled. We will end up with e raised to minus nx. We see that values of both LHS and RHS are same. So we must conclude that LHS is equal to RHS. Hence we say that this statement is proved. Let's go ahead for next example. Here we have to prove 1 plus tan hx upon 1 minus tan hx whole cube is equal to cos h 6x plus sin h 6x. Let us begin with solution. We consider LHS first, which is 1 plus tan hx upon 1 minus tan hx whole cube. Now we replace tan hx by sin hx upon cos hx. Then equating the denominator in numerator as well as denominator over here, we will have cos hx plus sin hx upon cos hx minus sin hx whole cube. Now let us replace cos hx and sin hx by its exponential form. So we will have something like this. This 1 by 2 you can take out common from numerator, similarly from the denominator. So this 1 by 2 from the numerator will get cancelled with 1 by 2 from the denominator. So we will have e raised to x plus e raised to minus x plus e raised to x minus e raised to minus x in the numerator, and e raised to x plus e raised to minus x minus of e raised to x minus e raised to minus x in the denominator. Further simplification will give us e raised to x in the numerator and e raised to minus x in the denominator. If we take this denominator to the numerator, we will have e raised to 2x in the numerator whole cube, which is same as e raised to 6x. Now we proceed to RHS. RHS is cos h 6x plus sin h 6x. Replacing it with its exponential forms, and then simplification will give us e raised to 6x. Once again, we see that values of LHS and RHS both leads to e raised to 6x. Therefore, LHS has to be equal to RHS. Hence, we say that this statement is proved. Now, let us go ahead with next example. Here, we are asked to solve the equation 17 cos h x plus 18 sin h x is equal to 1 for real values of x. Let us proceed for the solution. The given equation is this. Now let us replace cos hx and sin hx with its exponential form in this way. Since denominator of both the term is 2, we will take that 2 on the RHS. So we will have 17 e raised to x plus e raised to minus x plus 18 e raised to x minus e raised to minus x is equal to 2. But e raised to minus x can be written as 1 by e raised to x. So this can be written as this. Further cross multiplication will give us 17 e raised to 2x plus 1 upon e raised to x plus 18 e raised to 2x minus 1 upon e raised to x. That e raised to x will take to the other side. So we have 2 e raised to x on RHS. Now let's open these brackets. Now we have 17 e raised to 2x plus 17 plus 18 e raised to 2x minus 18 is equal to 2 e raised to x. 17 minus 18 is minus 1. 17 e raised to 2x plus 18 e raised to 2x is 35 e raised to 2x. This 2 e raised to x as it is. Now let us rearrange the terms. So we have 35 e raised to 2x minus 2 e raised to x minus 1 is equal to 0. This is a quadratic equation in e raised to x. Let us solve this. We can write this equation as 35 e raised to 2x minus 7 e raised to x plus 5 e raised to x minus 1 is equal to 0. I have just wrote that minus 2 e raised to x as minus 7 e raised to x plus 5 e raised to x. Now from these two terms, we will take out 7 e raised to x common. So inside the bracket, we will have 5 e raised to x minus 1. Once again, this term is common over here. So when we take it out, we will have 7 e raised to x plus 1 inside the bracket. Now we have factorized this equation in this way. So we can say that either 7 e raised to x plus 1 is equal to 0 or 5 e raised to x minus 1 is equal to 0. When we say 7 e raised to x plus 1 is equal to 0, we get e raised to x is equal to minus 1 by 7. And when we say 5 e raised to x minus 1 is equal to 0, we get e raised to x is equal to 1 by 5. But e raised to x is equal to minus 1 by 7 is an impossible value because e raised to x never takes negative values. Therefore, e raised to x has to be equal to 1 by 5. Therefore, x is equal to log of 1 by 5. So this is the real value of x, which is the root of this equation. I hope guys you understood how we solve this equation containing hyperbolic functions. Let us go ahead with next example. Here we are asked to find tan hx if 5 sin hx minus cos hx is equal to 5. Now let us go ahead with solution. In solution, we first solve this equation for the value of x. Then we can substitute that value of x over here to find tan hx. So here the given equation is 5 sin hx minus cos hx is equal to 5. Let us substitute exponential forms of sin hx and cos hx in this equation. So we get this one. Further simplification will give us 5 e raised to x minus 5 e raised to minus x minus e raised to x minus e raised to minus x whole divided by 2 is equal to 5. When we take this 2 on the other side, we will have 10 on the right hand side. This 5 e raised to x minus e raised to x contributes to 4 e raised to x minus 5 e raised to minus x minus e raised to minus x contributes to minus 6 e raised to minus x. Now, when we divide this equation by 2, we get 2 e raised to x minus 3 e raised to minus x is equal to 5. Further, we write e raised to minus x as 1 by e raised to x, and then we cross multiply to both sides. We get 2 times e raised to 2x minus 3 is equal to 5 e raised to x. Little bit rearrangement give us the quadratic equation in e raised to x. We will solve this the way we solved the earlier equation. So let us split this minus 5 e raised to x as minus 6 e raised to x plus e raised to x. You can take out this 2 e raised to x common from both the terms. So we have e raised to x minus 3 inside the bracket. E raised to x minus 3 is common in both the terms. So when we take it out, we get 2 e raised to x plus 1 inside the bracket. So either 2 e raised to x plus 1 is equal to 0 or e raised to x minus 3 is equal to 0. When we take 2 e raised to x plus 1 is equal to 0, we get e raised to x is equal to minus half, and the other part gives us e raised to x is equal to 3. Once again, we neglect this value of e raised to x as e raised to x is never negative. So e raised to x has to be equal to 3. So when e raised to x is equal to 3, tan hx, whose exponential form is e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x, can be written as 3 minus 1 by 3 upon 3 plus 1 by 3. Note that if e raised to x is 3, e raised to minus x will be 1 by 3. Now further simplification will give us 8 by 3 upon 10 by 3, that is 8 by 10, which is nothing but 4 by 5. So this is the value of tan hx if 5 sin hx minus cos hx is equal to 5. I hope guys you understood this example. Now let's go ahead with next one. Here we are given that if cos alpha into cos h beta is equal to x by 2 and sin alpha into sin h beta is equal to y by 2, then we have to prove sec of alpha minus I beta plus sec of alpha plus I beta is equal to 4x upon x square plus y square. So let's prove this statement if the given data is this. In this statement, we begin with LHS. So in solution, we take sec of alpha minus I beta part first. Sec of alpha minus I beta can be written as 1 upon cos of alpha minus I beta. This can be treated as cos of A minus B. And we know the expansion of cos of A minus B, which is cos A cos B plus sin A sin B. So this can be written as 1 upon cos alpha cos I beta plus sin alpha into sin I beta. Now we will use the relation between circular and hyperbolic functions, which states that sin ix is equal to I sin hx and cos ix is equal to cos hx. So this cos I beta can be written as cos h beta and sin I beta can be written as I sin h beta. So we get RHS as 1 upon cos alpha cos h beta plus sin alpha into I sin h beta. But given that cos alpha into cos h beta is x by 2, so we can replace this first real part by x by 2. And given that sin alpha into sin h beta is y by 2, so this sin alpha into sin h beta can be written as y by 2, and we get 1 upon x by 2 plus I into y by 2. Further simplification will give us 2 upon x plus iy. This is value of sec of alpha minus I beta. On the similar lines, one can prove that sec of alpha plus I beta is equal to 2 upon x minus iy. Now finally, we put these values of sec of alpha minus I beta and sec of alpha plus I beta in the LHS of this statement. So let's substitute. So LHS becomes 2 upon x plus iy plus 2 upon x minus iy. Now let's cross multiply these things. Then in denominator we will have x plus iy into x minus iy. It is like a plus b into a minus b, which is nothing but a square minus b square. But minus b square means minus I square y square, and I square is minus 1. So minus minus becomes plus. So in the denominator we get x square plus y square, and in numerator we will have 2x minus 2iy plus 2x plus 2iy. Minus 2iy and plus 2iy will get cancelled. 2x plus 2x contributes to 4x. So sec of alpha minus I beta plus sec of alpha plus I beta becomes 4x upon x square plus y square as required. Hence proved. I hope guys you understood this example. Let us proceed with next one. In this example, we are asked to prove that cos h raised to 5x is 1 by 16 into cos h 5x plus 5 into cos h 3x plus 10 cos hx. Let's prove this expansion. Here we begin with cos h raised to 5x. We replace this cos hx by its exponential form, which is e raised to x plus e raised to minus x upon 2. So cos h raised to 5x is e raised to x plus e raised to minus x upon 2 whole raised to 5. Here we will use binomial expansion. In fact, we will use the Pascal triangle in binomial expansion of this. So let's draw Pascal triangle. This is the Pascal triangle for expansion of a plus b whole raised to 5. These are the coefficients involved in the expansion. This 1 by 2 whole raised to 5 we will write first. Then a plus b whole raised to 5 can be expanded in this way. You can pause the video and check the expansion. Further, we simplify these terms. This e raised to 4x into e raised to minus x becomes e raised to 3x. E raised to 3x into e raised to minus 2x becomes e raised to x. E raised to 2x into e raised to minus 3x becomes e raised to minus x. E raised to x into e raised to minus 4x becomes e raised to minus 3x. Then after simplification and combining terms with similar degree, we get this thing. So this e raised to 5x and e raised to minus 5x are written in one bracket. 5 times e raised to 3x and 5 times e raised to minus 3x are written in one bracket. Similarly, 10 e raised to x plus 10 e raised to minus x are written in one bracket. Further, this expression e raised to 5x plus e raised to minus 5x can be written as 2 times cos h 5x, because cos h 5x exponential form is e raised to 5x plus e raised to minus 5x upon 2. Similarly, this expression can be replaced by 2 times cos h 3x, and this can be replaced by 2 cos hx. Now let us take 1 2 from this outside constant and divide it to this inside expression. So we will have 1 by 2 raised to 4 into cos h 5x plus 5 into cos h 3x plus 10 into cos hx. This is the required RHS. I hope guys you understood how to find out expansion of higher powers of hyperbolic functions. In my next video, we will see more examples on hyperbolic functions. Till then, keep watching. Thank you all of you. Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.